Hello and welcome to a new video. This is for Precalculus using the Math-UC curriculum. We're on lesson 23, which talks about graphing, sine, and cosine. So I don't know if you thought we were done with trig, but we're not quite done. We got a little bit more to do. Now, as we graph functions in general, there are ways to do that where you don't have to rely on a calculator very much or don't have to rely on making a table of values very much. But if you don't know how to graph something, those two tools are what you can use for any function, your calculator or your table of values, with the caveat here that it's hard to put some things in the calculator and it sometimes is hard to get a table of values. I'll give you that. But I am going to walk through on these some things about them that we can do where we can look at the equation and know what it looks like, because these rules actually go for all functions. That's actually why one of the reasons why we care if something's a function or not, because there's these set of rules that work for all functions, and it's really cool. So just keep that in mind. I don't know if you've actually seen a sine or cosine curve at this point, so we're going to start off just by graphing regular sine and regular cosine. What I mean by that is there's no extra numbers in either of them. It's just y equals sine x, y equals cosine x, and these are called the parent functions for sine and cosine because then anything else you do that has a sine or cosine is some version of these two graphs. If you are using your calculator for this, you'll want to be, or it's a little bit easier to be in radian mode than it is to be in degree mode. You technically can graph in either, but one of the tools that will help you on your TI calculator is to use zoom trig. So you press the zoom button and then Z trig is an option, because then that adjusts your window to something that makes sense for using trig functions. So it actually does two things. If you're in radian mode, it zooms you to negative 2 pi to 2 pi and then makes your tick marks be pi over 2 apart. And then if you're in degree mode and you zoom trig, it should make it be from 360 to negative 360 or 720 to negative 720. I don't know. I just don't normally graph in degree mode. So, but it should adjust your window appropriately. So let's go ahead and get started here. When we graph y equals sine x, I'll go ahead and I'm going to graph it on Desmos and bring it over here for you to see. And then we can basically kind of talk about some things happening here. So this is in radian mode because I just opened it up. And so when we're in radian mode, we graph y equals sine x, we can notice some things. Sine starts at 0, 0, and then goes up to the right, down to the left. If you were to zoom in really close here on sine, this is kind of random. It looks like a line, but you have to zoom in pretty far to make that happen. Because really, sine is a curve. It goes up and down, and it repeats this pattern forever and ever and ever. So it starts at 0, 0. It goes up, and this top point here is actually at pi over 2 for x and 1 for y. And then it comes back down to 0. It does that at pi. And then it goes to negative 1 at 3 pi over 2. And it comes back up to 2 pi comma 0. If we are making a table of values for this, we actually use the unit circle because whenever we do, when we look at the angle 0, sine is the y value, which is 0. When we look at pi over 2, the y value is 1, and so on. Some interesting things about this. This is a function that oscillates. It goes back and forth, back and forth. It never, no matter how far you go to the left or to the right, ever goes above 1 or below negative 1. So it just keeps on going between those two things. And so because of this, these are really good at representing waves, because this is how different types of waves, we have sound waves, light waves, microwaves. I mean, I think microwaves have waves, but anyway, that's something that goes up and down like this. So for us to graph this here, I'm going to start at 0, 0. And then I'm going to, at pi over 2, be at 1. And then at pi, be back at 0. 3 pi over 2, be at -1, and at 2 pi be back at 0. I can continue the pattern backwards here. And then attempt to make this look curvy, which since I'm drawing on a computer, I'm sure this is gonna look great. This is not so bad so far, but it could really go downhill. Oh, that was actually not so bad. Okay, some things that I want to point out that we care about for our sine and cosine functions or our trig functions in general. This amount that we go up or down, so the amount from the middle to either the top point or the low point, that is called the amplitude. And those should be the same distance. Like however much it's going up from the middle is the same as how much it's going down from the middle. And that's a special property of this that we call amplitude. So in this case, for a regular sine that doesn't have any other numbers or things in it, our amplitude is 1. Another thing we look at with trig functions is called the period. And this has to do with the fact that if we kind of like just think about from 0 to 2 pi, that has done a complete sine curve. It's gone up and then it's gone down. And so all of the values for sine actually happen between those two places, and then it's repeated over and over and over both directions forever. So this idea of how much does it take to get a single part of our sine curve, that is called the period. And so normally sine has a period of 2 pi. So there's things that we do to functions to change the graph. So some things we can do is we can stretch them vertically. So we can make it so that our amplitude is bigger. We can also shrink them vertically so that our amplitude would be smaller. We can stretch them horizontally, so that would make our period bigger, or shrink them horizontally, which would make the period smaller. The other thing we can do is we can shift the whole graph up or down or left or right. The Matthew C book uses the word translation, which not just the Matthew C workbook does this, but specifically with trig functions, when we're moving up and down, we call that a translation. When we're moving left to right, we have a special word for that called a phase shift. That we don't use the term phase shift for non-trig functions. Normally for like any other function, we just say translation left or right or up and down. But for this, we have a specific phase shift thing that's happening. So this is what sine looks like. The other thing we can do is reflect this. And so that would make it go down to the right instead of up to the right. That happens by putting a negative basically in front of sine. So let's look at cosine. When I graph cosine, it's going to change this just a little bit. And in fact, if you're not paying attention, you might not even realize what's different about it because they basically look the same. Instead of starting at 0, 0, we actually start at 0, 1. And then we go down, and at pi over 2, we're 0. At pi, we're -1. 3 pi over 2, we're 0. And at 2 pi, we're back at 1. So this is what we would consider to be like one period of a cosine curve from 0 to 2 pi. We still have an amplitude of 1. We still have a period of 2 pi. The difference is basically that cosine is shifted over pi over 2 from where sine is. So that actually means that if you were trying to model data using a sine or cosine function, you can pick either one. It just, whichever one you pick, like there's a shift involved that you'd have to think about. So let's graph this on our paper. So we start at 1, then go down to pi over 2, go down to pi, go down to 3 pi over 2, up to 2 pi, and then I can continue that pattern backwards where I just oscillate between -1 and 1. For me, cosine is actually the harder of the two to make look curvy, and it seems like that's true for most students as well. It's a lot easier to make, like you're a lot more likely to miss that point, to make it look like a V instead of something curvy. So just so you know, pretend I didn't miss that point. Because otherwise this looks like a actually really good cosine curve for drawing on the picture. Drawing on the computer, I mean. So just like with sine, we have this idea of amplitude, and our standard amplitude for cosine is 1. we have this idea of period, that how long does it take to do a whole cosine curve, which is going to be 2 pi. And again, we can do all the same things. We can stretch this vertically or horizontally, shrink it vertically, horizontally, or just move it around to different places and get different graphs because of that. Now, the way we can tell what's happening the way we can tell what transformations are happening is by looking at the equation. So I have like a formula kind of up here at the top where I have A, B, C, and D that would represent numbers. Now, typically you won't have all of these at the same time, or at least not at first. You'll like start off with one of these happening, and then maybe it'll go to 2 things happening and just kind of get more complicated as you go. So I've listed here like what do each of these things tell us. So if A is positive, then it's a standard sine or cosine curve. If it's negative, it actually will like go down first for sine or start at the bottom amplitude if it's cosine. The Math You See workbook doesn't give us any with negatives in front. I just felt like telling you what that would do. The absolute value of A, so if there was a negative in front, we'd ignore it for this next part. We'd say whatever that number in front of sine or cosine is giving us the amplitude of the graph. So if we see 5 sine x, the amplitude isn't going to be 1, it's going to be 5. So you're going to have to go up to 5 and down to -5 for your graph. Then that's going to be if there's a number in front of sine or cosine. If there's a number that's in front of the x in the formula, that number would be inside of your sine or cosine function, and it's affecting x. So what that does is it actually affects our graph horizontally. So it affects the period. And the way we figure out how that works is whatever number is in front, we do 2 pi divided by that number, and that tells us what the period should be. So that tells us how long it takes to do an entire sine or cosine curve. And I have an issue with, so my Math You See workbook and teacher book are actually kind of older. So it may be that this has been fixed in a more recent edition. I really don't know. But it seemed like there was an issue happening where the Math You See workbook was calling the number in front of x the period, and that's not true. If you have a 2 in front of the x, then that's saying that what you're going to do is 2 pi over 2 and get pi. So instead of going 2 pi to get a whole sine curve, you just go to pi and get a whole sine curve. So that means your graph is happening twice as fast, and that we've like shrunk our graph in horizontally. And so it looked to me like the workbook was just wanting you to say, okay, if the period is 4, I put a 4 in front of x, and that's not actually how that works. But we'll go into that a little more later probably. C, which is inside our parentheses, if it's being added or subtracted to x, that's our phase shift, our shift left or right. I have a negative in the formula because when you are talking about things that are affecting x inside of a function like this, it actually does the opposite of what you think it would. These things are part of the super secret opposite society. So that b in front of x, actually you want to think of the reciprocal to think of whether or not it's shrinking or stretching your graph horizontally. So a 2 in front, if I flip that, I get 1/2. It actually shrinks our graph in, so it's half as big as it was before. If I have like x plus pi, well, instead of thinking that plus pi would mean right pi, because plus is right for x, it actually makes it move left pi. So anything happening inside of our sine function actually does the opposite of what it would do if it was outside. The plus d at the end is going to shift our graph up or down, so it ends up changing what our kind of center anchor point that we're oscillating around is. Now, this may be something that you should just come back to after we've graphed a couple, because then it might make more sense. But we are going to graph, we're going to start with some that are pretty simple and make them more complicated. And just know that for any of these, really, you can go ahead and use your calculator to help, use the solutions to help, make a table of values. But as you're doing that, it is helpful to kind of go, okay, why do I think this was the way it was? Do I understand now that I've seen the answer where these numbers come, like, are actually in the graph. And then that helps you build this, like, kind of math gut instinct about, you know, looking at an equation and knowing what the graph is going to look like. And the main difference between sine and cosine is where cosine starts. Sine starts in the middle and goes up when it's positive. Cosine starts at the top amplitude, goes and then goes down. So that's going to help us to graph these different functions that we have. So we're going to start off with things that are relatively easy. I have a graph here that doesn't have any scale to it, because the easiest way to graph these actually involves us basically making the scale fit what we have. So that's why there's not any labels on this. Whenever we look at this, we look at, okay, how is this different from just y equals sine x? There's a 2 in front. And we think, what is that 2 going to do? In general with functions, if you are multiplying by a number outside the function, so outside of sine, not inside of sine, what it does is it vertically stretches or shrinks your graph. So this 2, because it's a number bigger than 1, was going to vertically stretch our graph by 2. In the case of trig functions, this actually has a term, amplitude, that we can use. So this is actually saying that our amplitude is 2. So we're going to end up going up to 2 and down to -2 for our graph, instead of going up to 1 and -1. The other thing we'd look at for trig functions specifically is there anything in front of the x that is affecting the period? Because if there's not, then the period is going to be our standard 2 pi. So if that's the case, if our period is 2 pi, then the easiest way to graph this is to make each of these tick marks be pi over 2. And so you can kind of use the quadrants of the unit circle to help you with that. So our sine graph always starts at 0 unless we've shifted it up or down. Always, except sometimes. We want to go up to 2 and have that happen by pi over 2. So that's going to be right here. Then we want it to come back down and hit pi. So pi is 0. We want to go down to -2. We want to come back up to 2 pi. So to be kind of clear here on this, our scale is different for x and for y, because for x, the most convenient thing is to actually use pi over 2 pi, 3 pi over 2, 2 pi. But for y, we're actually still getting a mixture of kinds of answers, but we can get nice answers for some of these values. So our scale for y is actually going by 1. So 1, 2, 3, -1, -2, -3. We can go backwards and continue the pattern. So 0, 0, we'd go down, then come up, then go up, and then go down. And so this is just a pattern that's happening. And then we try to draw this in a way that looks like a sine curve. Hopefully your sine curve looks at least the end of that really took a turn. Boom, ching. Hopefully yours looks at least as good as mine. But that's the idea. That's what that 2 is changing. If you compare this to what y equals sine x looked like, the only difference is that it is stretched vertically so that it goes up to 2 and down to -2 instead of up to 1 and down to -1. You can graph this on your calculator and have that help you. You just type in y equals 2 sine x, and it should graph something that looks like this. Let's look at another example. So this one says y equals cosine x plus 1. So there's not a number in front of cosine or in front of the x. So our amplitude is our standard of 1, and our period is our standard 2 pi, which means the scale we want to use is going to mean 2 pi ends up right here at our 4th line. And the scale up and down is going to be just by 1s. Now, if this was a regular cosine without the plus 1, we'd start up here at 1. This is not what it's going to end up looking like, so don't draw it yet if you're going to be mad about having to erase it. This is what normal cosine would look like, but this plus 1, which is outside of our function, if this was inside of cosine, they would have to put parentheses around it to show that, and they didn't, so that's not what's happening. This +1 is affecting our vertical location. So I'm going to take each of these points and I'm going to move them up one spot. So we'll still be able to see what our original cosine looked like, right? It's down here, but this cosine that we're graphing has been shifted up 1. So all of our points are going to, instead of oscillating around 0, they actually oscillate around 1. Our amplitude, which is 1, now what we're looking at is, that doesn't mean it's going up to 1 and down to 1. It means that from our center here, that's what we're going up 1 and down 1. We've shifted up. What are we oscillating around? But our amplitude is actually not any different than our normal cosine curve. So we're going to connect this and draw it. I feel like there was something I was going to say. I think I'm just going to point out, like, whenever you're doing, if you type this in on your calculator will, I don't know why this curve keeps getting me here. Your TI calculator opens up a parentheses whenever you press cosine. You want to put the X and close the parentheses and then put the +1. Mathematicians are lazy, so we know that we don't really need the parentheses around this X to get our point across, but for our calculator, the calculator needs to know very specifically, okay, what are you saying is inside of cosine? And we do that with the parentheses. That +1 should not be inside the parentheses because we didn't have parentheses on the problem. So this is our answer with a little extra curve there. So there you go. Example 3. Now we've got two things happening to this sine curve. We've got a 1/2 in front, which is going to affect our amplitude. Our amplitude is 1/2, which means that our graph is only going to go up to a half and down to a half. It's going to go half as high and half as low. This 2 inside is affecting the period. What we do is we say 2 pi over 2. The 2's cancel and get pi. So the period of this is pi. There's two ways to handle this as far as what our graph looks like. We could make it so our scale has just moved, and we could make this be pi instead of 2 pi. And what that does is it means that our pattern fits. I'm going to actually graph this two different ways to show you, so you can keep that in mind. You can decide which way you like better. If we put pi here, then as we're drawing sine, we start at 0, we come up to a half, go down to 0, come down to a half, come up. So it's not as obvious that in some ways that we've shrunk this horizontally, because all we've done is changed our scale so that that this is happening by pi instead of 2 pi. That's one way to graph it. If you wanted to do this a little differently, or I guess that would be doing it different. If we wanted to still have this be 2 pi, then that means that pi is right here. That means that we're going to end up doing an entire sine curve by this point pi. So what that does is that makes it to where we can actually show, hey, this has shrunk because it's gotten closer because we're doing a whole sine curve by pi, which means that we will have done 2 sine curves by 2 pi. You don't have to make this many sine curves. I just like drawing them, even though this is going pretty poorly on the computer. It's fine. But that's kind of what it looks like. So you have options there of, do I want to make my scale feel more accurate by keeping the 2 pi over there, and then our graph, we end up being able to fit more sine curves? Or do we want to make it easier on ourselves? Or do we maybe want to make it easier on ourselves by stretching out our scale? Either is fine. And just to make sure we're clear here, I only went up to a half and down to negative a half because of the 1/2 in front of sine. Now I kind of accidentally only did, maybe not only did shifts on cosine, but that is the thing that's happening here, is that example 2 and example 4, which were both cosine, both had shifts, and I didn't. Example 1 and example 3, which had sine, did not. So that is just an accidental thing. That's not actually like we only shift cosine up and down, not sine. There's three things happening here. And so it's kind of at this point when we start having three things happening, that means that we're going to have multiple things affecting our graph vertically or horizontally, and that's really where things can get complicated. Vertically is not as bad as horizontally. You can trust me on that, or you can wait until the next example to see what I mean. So the 3 in front means our amplitude is 3. The 1/2 in front of x, this is a part of the super secret opposite society. So we'd flip this over if we're thinking about what's happening to it. We'd say this is really like a 2. This is actually stretching our graph horizontally so that it takes twice as long to do a whole cosine curve. Now, to actually figure out what that means for the period, we do 2 pi over a half. To divide by a fraction, we actually want to multiply by the reciprocal. So this gives us 4 pi. So instead of doing a whole cosine curve by 2 pi, it takes 4 pi to make that happen. I didn't even think about this when I did this in class. We could still make this be 2 pi, which means we'd only actually do half of the cosine curve by the time we got to 2 pi. But my personal preference is instead to make it 4 pi, because I just think it's easier to picture that way. So I would make this be 4 pi, which means this is going to be 2 pi. We're going to do a whole cosine curve by 4 pi. But we also are shifting this down 1. So instead of our cosine curve oscillating around the x-axis, it actually is going to oscillate around -1. This would be -1 that it's oscillating around. So how do we do that? And also there is a scale issue here because I'm going up and down 3, which there's 3 tick marks up and down. But if I shift this down 1, then all of a sudden I'm going to be off of my graph on some of these points. So either I could make my scale be by 2s, or I could just, since it's pretty close to being on the graph, you could graph it with these being 1 and just kind of make it be just a little bit off the graph. I'm going to do the scale by 2s here. So what's happening for cosine is we start off at the top amplitude. So we start off normally at 3, but I want to shift this down 1. So our first point is actually going to be here at 2. And we're basically going to keep this going. If I draw what cosine would look like without the -1, it'd start at 3, it'd come down here to 0, then it'd come down here to -3, then it'd come back up to 0, then it comes back up to +3. All of these need to be shifted down 1. So that gives me this 3 moves to 2, this 0 moves to -1, this -3 moves to -4, this 0 moves to -1, this 3 moves down to 2. So here is our cosine curve right here. So, like I said, this is kind of a lot to really think about. I get that. Whoops. There's a lot to kind of think about and wrap our heads around. So, the Math U C workbook actually, like A and B, I think, like limit it to kind of like 2 things happening at the same time at most. And then C and D, it gets more complicated and throws in like phase shift and things like that. So hopefully what happens is that you don't just do all these the night before they're due. You actually do A and try to like figure out, okay, what's happening whenever I just have 1 or 2 things. Then you do B, get better at it. And you do C, which maybe adds some complexity. And so you're just like, okay, this is fine. I'm going to, keep going and then D, and hopefully by the end of it, you're like, oh, okay, this has gone really well. So I do have 2 more examples here, but really these end up getting complicated. So even though this only has 2 things, because I have just a half and a pi over 2, because both of these things are affecting x, this is just like the thing that is a struggle for graphing functions without your calculator in general. So even if this was like a parabola or a square root function or whatever, if there are 2 things affecting it horizontally, it gets complicated. if you put this into your calculator, sine opens up a parentheses, which I used to bracket for funsies, but sine opens up a parentheses. Then you type in 1 divided by 2. Then you'd open up a parentheses and then put x plus pi over 2. And then we could either choose to close our parentheses or not. That's going to annoy some people, but I don't care. Because as long as there's not supposed to be anything else after the parentheses, you don't actually have to close parentheses on your graph. So this 1/2 in front of our parentheses with x is going to tell us what's happening to the period. And it's actually the same as what happened to us in example 4, that this is 2 pi over 1/2, which means the period is 4 pi. The amplitude of this is 1, but this is telling us that we are shifting to the left pi over 2. You might be thinking right pi over 2 because it's affecting x and it's positive, but it's inside of our function, and so it's actually doing it the opposite way of what we might think. So it's going left pi over 2. So let's break this down. If it just was the shift of, not shift, if it was just one or the other, this would not be too terrible to graph. But because it's both, we have to think through this. I'm going to actually think through this 4 pi first, and then I'm going to move everything to the left pi over 2. One of the reasons this ends up being difficult is because if this is 4 pi, this is 2 pi, this is pi, this is 3 pi. If I move all of my points pi over 2, that's actually like going to be half a tick mark. So keep that in mind. So normal sine with a period of 4 pi, so that's not actually normal, is going to go up to pi, or up to our top amplitude at pi, in the middle, down here, back in the middle. But we want to shift everything to the left pi over 2. So this point is going to move here. And this one is going to move here. This one's going to move here. This one's going to move here. This one's going to move here. And then we could erase our other points so that we don't get confused. So that's kind of how I deal with it. Is okay, it's easier to deal with the period part of this first, and then to take that and shift it. So that is sine of 1/2 parentheses x plus pi over 2. So on this example 6, we've got all of the things happening. We've got a vertical stretch of 2. So it's going to go up to 2 and down to -2, except wait, we also are shifting up 1. So it actually is going to go up to 3 and down to -1. I shouldn't have put that point there because we have 2 other things happening. We've got this 4 in front, which is going to make our period be 2 pi over 4, which simplifies to be pi over 2. So we're going to do a whole cosine curve by pi over 2. That's really, really fast. So if you make these tick marks each be pi over 2, that's actually kind of fun in some ways. Like, we do a whole cosine curve by pi over 2. We are also, though, shifting to the right pi over 2. So actually, those two things kind of make each other not, like, the right pi over 2, since we do a whole curve by pi over 2, that actually means that, like, it just shifts it over a period, so it's going to look the exact same. That was not intentional on my part. So if I want to do it, like, with pi over 2 here, well, I'm going to start my cosine at its top amplitude, which is 2 plus 1, which is 3. And then it's supposed to be back at its top amplitude by pi over 2. So in the middle here, let's see, it's going to be down 2 from 1. So it's going to go down to here, and then it's going to be here and here. So it's very difficult to make this look good on the computer, or probably even on your paper. So that's really, really bad. Let's let Desmos show us what it's actually supposed to look like. So 2 cosine. So on your TI, you're going to it's going to open a parentheses, then you're going to have to open another parentheses to make this work. See how squishy it looks? Oh, see how squishy? Compared to, I guess, like, it's kind of neat to go ahead and put them together. Like, this is what a normal cosine looks like in blue, but look at all the things we've done. We've stretched it up by 2. Oh, this is not supposed to be inside. We've stretched it by 2. We've shifted it up 1. We've also moved it so that it's squished horizontally. We've shifted it over, although that didn't end up mattering because it was shifted over by the same amount as its period. So that's how that goes. So in the Math UC workbook, there's 3 types of problem. The first is there's like 6 graphing questions. Then there's 2 questions where they give you information and ask you to write the formula. So this is where I had an issue with on a problem. It said that if the period is 4, but then in the answer book, it had a 4 in front of x. That is incorrect. If the period is 4, that's not the same as saying put a 4 in front of x. So maybe that's been fixed more recently, maybe not. I told my kids that they could skip those 2 questions if they wanted to, or they could just look at the solutions and rely on that. But there is that issue here. What they should do instead is say things like, oh, the period is 4 pi. So that means that we need to say 2 pi over what gives me 4 pi. That ends up being a half. So you'd put a half in front of x. That's how that's supposed to work. It's complicated. It's more complicated that way. But that's how that works. Or they should have just said, hey, the number in front of x is supposed to be this number. But calling it the period is incorrect. Then the last section, they give you graphs and want you to write the equation. So I would imagine that would go a little better because you can see the period and then know, okay, I need to do 2 pi over b equals whatever the period is. And that gives me the number in front of b. Thanks so much for watching. Hope you enjoyed this. I'm trying to do like fun things on my YouTube channel, and it would really help me out if you subscribe and like the video. And when you're watching this, there may be a little like join button as well as a subscribe button, so you can join and be a member of my YouTube. And there's some perks that go along with that if you're interested. But it would help support me and help let me continue to make videos so that I can help you with math forever and ever and ever. So yeah, thank you and bye.